Upgrading a fabric can introduce risk if dependencies or configuration issues are not identified early. In Cisco ACI 621, the upgrade workflow is redesigned to validate conditions up front, execute tasks more efficiently, and provide continuous visibility throughout the process. Key enhancements include support for SIMC upgrades directly from the controller, earlier detection of failures, and improved monitoring across the entire upgrade lifecycle. I'll start by navigating to the firmware section and selecting controllers. From here, I can initiate upgrades and also review previously completed upgrades, including their status. In addition to controller upgrades, SIMC upgrades can also be managed from this interface, providing a more integrated workflow once the image is available. For the controller upgrade, I'll select the target version and move into the validation stage. As part of this process, the system automatically runs pre-validation checks to ensure the environment is ready. Validation rules can be retrieved dynamically from Intersight or from the local repository, with fallback handled automatically if external sources are unavailable. If validation rules cannot be retrieved from any source, the system treats this as a catastrophic failure and blocks the upgrade from proceeding. In addition, critical configuration checks are performed, and any failure classified as catastrophic immediately stops the upgrade to prevent risk to the environment. To demonstrate this, I'll introduce a failure condition by disabling the global AES passphrase, which is required to ensure encrypted backups are available for recovery. When I run validation again, the system detects this as a catastrophic failure and prevents the upgrade from proceeding. A clear message indicates that all catastrophic issues must be resolved before continuing. Once the issue is corrected, I can rerun validation. With all critical checks cleared, the system allows the upgrade to proceed. Moving into the upgrade workflow, I now get a detailed view of the process across both cluster level and per-node execution. Tasks that do not depend on each other, such as preparation and early validation stages, are executed in parallel across nodes, reducing overall upgrade time and allowing issues to be detected earlier. When the actual upgrade begins, node-level operations are performed sequentially to maintain cluster stability. As the upgrade starts on the first controller, that node begins its reboot process and becomes unavailable. Control is then transferred to another active controller. The interface automatically redirects to the next available controller, and the upgrade workflow continues without interruption. The session remains within the same upgrade view, so there is no need to manually reconnect or navigate back. As the next controller begins its upgrade and reboots, control shifts back to the first APIC that was successfully upgraded. From that point onward, the upgrade progress of the remaining APICs can be monitored directly from the first upgraded APIC, eliminating the need to switch controllers again. In parallel, the system provides a detailed timeline for each stage. It shows when each phase starts, completes, and transitions, allowing the progress of both cluster-level and node-level operations to be tracked clearly. As nodes complete their upgrades, the process continues sequentially until all nodes are upgraded. Final validation is then performed across the cluster, and the upgrade completes successfully. Validation reports can be downloaded as a full report or at an individual rule level. Previous upgrades can also be reviewed to understand historical activity and outcomes. This demonstrates how ACI 621 enhances the upgrade experience through automated validation, early failure detection, parallel execution, and continuous visibility, allowing upgrades to be performed more efficiently and with greater confidence.